Okay, here's the proof for Math 117 Class 13, and I'm going to preface this with a comment about bounded sequences that don't converge to anything. So let me draw some lines. That's an upper bound. That's a lower bound. And here are some intermediate lines. So here's the deal. I'm now going to show an infinite sequence of values Okay, you got the idea. This sequence does not converge to any limit. However, we can always make an increasing sequence that converges. How do we do it? We say, well, here, what's the smallest value that we'll ever see? It's this one. Now we come to here. What's the smallest value we'll ever see? It's this one. And here are more of them. And you'll notice at every point, one of these circles indicates the smallest value that can ever occur. And this increasing sequence of numbers converges to the lim inf of this sequence. Similarly, I can ask at the start, what's the biggest value I'll ever see? It's this one here. And when we get to here, it's that, then that, then that. And beyond that point, the largest value is always below that line, which is the lim sup. So, any bounded sequence has a lim sup and a lim inf. If the sequence converges, these are both equal and they're both equal to the limit, and no one talks about them. Okay, now I'll get to work on Fatou's lemma. Fatou's lemma says if you're thinking about a sequence of random variables and their expectations, the lim inf of the expectation is greater than or equal to the expectation of the lim inf. And in order to prove it, I start by defining formally a variable zn, which I was talking about in my example a minute ago. I will look at the infimum for m greater than or equal to n of xm. In other words, I'll look just at the tail of the sequence and ask, what's the smallest value that shows up if I go beyond the nth entry? Why is this useful? Well, I'm now going to convince you that this z sub n is an increasing integrable random variable. This is a bit fussy. Remember that with a random variable, we always want to be able to figure out the probability that it's less than or equal to a. So we ask, under what conditions, for what omega in the sample space, is z sub n of omega less than a? And the answer is that's going to be true if and only if there exists some m greater than or equal to n for which the mth random variable evaluated on that omega is less than a. In other words, the event, the smallest value that's still to come is less than a, is the union of all the events. Upcoming events have a value x sub m of omega that's less than a. Okay. Now, let's look at the inverse image of that. The subset of the sample space for which z sub n is less than a is the union of all the regions in the sample space that lead to an x sub m that's less than a. Okay? We are told that the x sub m's are all integrable random variables. So each x sub m is integrable. And a random variable can't be integrable without being measurable. Okay, since x sub m is measurable, what does that mean? It means the inverse image of the interval that goes up to a is in our sigma field. And since countable unions of things in the sigma field are also in the sigma field, this countable union that we just formed is also in the sigma field. Furthermore, intervals of this form generate the Borel sigma field and so z sub n is Borel measurable. Now, why is z sub n better than x sub n? Well, notice when we constructed our z sub n's here, we came up with a nice increasing sequence that converged to the lim inf, even though we started with a sequence that didn't converge at all. That's what happens for each individual omega, and it also happens for the random variables. I can say for each omega, z sub n is less than or equal to x sub n. And since we know that x sub n is integrable, z sub n is also integrable. Now let's think about an individual omega in our sample space. What happens to z sub n of omega? Well, the z sub n of omega are like these circled points, and it converges to the lim inf of x sub n of omega. Why is that true? That's the definition of lim inf. Well, the monotone convergence theorem applies in this case because z sub n is an increasing, hence monotone sequence, and it converges to the lim inf of x sub n. In other words, the limit of the expectation of z sub n is the expectation of the lim inf of x sub n. That's the monotone convergence theorem. It says that if we have a monotone sequence of random variables that converges almost surely to a limit, the sequence of expectations converges to the expectation of the limit. In this case, it's also true that each individual x sub n is at least as big as z sub n, because z sub n was chosen to be the smallest of the x sub n, and therefore the expectation of x sub n is likewise greater than or equal to the expectation of z sub n. Now, as our final step, take the limit of both sides as n approaches infinity. Deneen always writes n approaches infinity, but in sequences, n always approaches infinity, so I don't take the trouble to write that down. Well, z sub n is increasing. The expectations form an increasing sequence. If a sequence is increasing and bounded, it converges. And what does it converge to? Well, if I take the lim inf of the expectation of z sub n, since it converges, that lim inf is just equal to the limit. And z sub n is the infimum of the limit of x sub n. So that is equal to the lim inf of x sub n. And now, remarkably, we are done. I can say on the left-hand side, okay, I'm going to take the lim inf of both sides of this. So the lim inf of the expectation of x sub n is greater than or equal to the lim inf of the expectation of z sub n, but since z sub n converges, the lim inf is just the limit, and we have shown that that limit is the expectation of lim inf of x sub n. Of course, Deneen doesn't like to write it that way. What he writes instead is the lim inf of the integral over the entire sample space of x sub n dp is greater than or equal to the integral over the entire sample space of lim inf of x sub n dp. Finally, what happens if x sub n actually converges? Well, in that case, the lim inf and the lim are the same, so the lim inf of x sub n is equal to the limit of x sub n, and we're calling that limit random variable x, and our conclusion in that case is that the lim inf of x sub n dp is greater than or equal to the integral over the sample space of the limiting random variable x. You want to go back and look at sample problem 1 now to see how this shows up in a real example, and then there are 2 more nice examples that I've dreamed up for the workshop.